Welcome back. Today we're going to talk about analyzing data from lab number 1 that we've done, which is our pendula on parade, right, where we're looking at the relationship between the period of a simple pendulum and the length of the pendulum. So there are two parts to what we'll talk about in this video, particularly since all of the seniors are absent this year for the Senior Day of Recollection. The first part of the video will talk about how to do a good graph by hand, which is a skill that you need to be comfortable with because it's often, not always, but often, a question on the AP Physics C exam. And then for the second part, we'll work on the analysis. So for the guys who have had me before in honors physics, you might find that you're already comfortable doing the graphing by hand part and you skip to the analysis. Otherwise, let's go ahead and work through those pieces. So I have here the data compiled from the two classes put together. I've also made a graph using Excel, and we can see that, that's a pretty quick and easy process. So the first thing to talk about, why even graph by hand? Right, the first thing is to make sure that you understand how you set up a graph. Oftentimes in math class, your scales are the same earlier on, like in Algebra 1, and so we don't get comfortable working with graphs that have different scales and how to make a good scale for our graph. The second piece is that you really want to be comfortable knowing, well, when do I make something, when is something linear, when it is not, how do I deal with something that's non-linear, what is that process to linearize something that is not linear, and then thinking through the meaning of all the parts. What's the meaning of the slope, the y-intercept, and the overall equation that results from this graph? So the first thing we'll do is work through how to make a good graph by hand. Now remember, what we are plotting here is the period squared on the vertical axis versus the length. That's what we had to do in order to linearize. So what I'm going to do now, I'll pause the video, I'll plot by hand, and I want you to do the same thing. Come up with a scale that fits the graph paper that looks like this that I gave you in class. What is a scale that fills more than half the page but doesn't make your life miserable? And we can talk about how you might think through what would be the best graph. So the first thing I'll do is just take all of this data, make my life a little easier, and well, I need to enable editing. So generally what I like to do, if I can, is take data and write it in order from least to greatest, and that usually makes life a little bit better in terms of graphing. And now I'm just trying to make Excel sort the way I want to. Expand this selection. Okay, so for my vertical axis, I need a scale. You should always start from 0. That way you can see the shape. Always start from 0. So that's rule number 1. Always start from 0 for both axes. And I need to go up to 2.25. So for my vertical axis here, if you haven't counted already, I believe there are 50 boxes that go up. So the question is, how do I fit 2.25 into 50? So instead of doing 2.25, what I like to do is just get rid of the decimal point. And I'll just write on this graph paper and erase it. Let's say instead that I have 225 that needs to fit into 50. What is something that can fit that makes my life easy? Now 225 divided by 50 is 4.5. So that would mean that I could make every line 4.5. So when I talk about making a scale that's easy, this is not an easy scale. What we can do instead is round that up to something a little bit better, and I could make every line instead 5. And that's something that's a lot easier to work with than the other case, right? Okay, so now the question is, what do I do with the decimal point? Well, in reality, the last point is 2.25, right? So I've moved the decimal point over 2. So instead of every line being 5, I want every line to be 5, move it over to 0.05. And if we do 0.05 in our calculator, 0.05 times 50, just to make sure we go up to 2.5. And yeah, that works, right? You can't double it, so we don't have to worry about that. That's good. And it's an easier scale to work with. So let's go ahead and make that scale. Now, I've marked out part of the scale. You don't need to mark out all the lines as long as you're consistent. But before we move on, we need to make sure that we label what is our variable and what is our unit. So make sure you're comfortable with what is the difference between those. I can't tell you how often that gets mixed up. Variable is what is you changed. Unit is what you use to measure that thing that you changed. Like so the period is what we changed, right? And we squared it. So this is the period squared. And the unit we used to measure the period was seconds. So since we squared the period, we have to square the seconds. So sometimes there's a point for both a scale and a label. Sometimes on the AP exam there's a point for the scale and another one for the label. Please do both. It's really just overall a good thing to be doing for your graph. Right. So now what we need to do is do the horizontal axis, right? So again, we do the same process. We look at our data and we go, okay, what is the biggest number that we have? And it is this number here, 57. So the question is, how do we fit, well, 0.57, right? How do we fit this number of 0.57 into this bottom range? This time we only have 40 boxes. So again, if I just took 0.57 and punch it into my calculator, 0.57 divided by 40, we get this 0.01425. Not a really good scale. And again, let's do instead 57 divided by 40 just to keep this better in mind. So it's 1.425. So I could do every line as 1.5, and that fits pretty well. My only hesitation with 1.5 is it's pretty hard to break down. So instead what I might do is make every line 2. Or, right, instead of 2, I need to do 0.02. So that way if I do 40 times 0.02, I end up with 0.8. I can't double the scale, but it should cover most of my graph. So let's do that now. Now I stopped at 6/10 because I don't need to go past that, right? My biggest value is 0.57. And again, we need to label. So this time I'm plotting the length in meters. All right, and then it's a good idea to do a title. What I like to do for a title is first, what am I plotting, right? I am plotting my period of oscillation squared versus my length for a simple pendulum. Apologies for the bad handwriting. Not much I can do with the touchpad here. But period squared versus length for a simple pendulum. That is what we are showing here with the data. So now the process is just to go through and plot our data. So that's what we have to do now. All right, so I've done a rough sketch by hand. I will, time to time, refer to our actual graph just because I did not anticipate how difficult it was to graph on this laptop, in part with zooming in and out. But I've done my best just to give us a means of discussion here. So we have the data plotted, and now this time the data is really, for the most part, looks linear, which is our goal, right? So now that we've plotted the data, let's talk about what do we do next. And the goal is, since it's linear, to get an equation and a slope for this set of data. So we have to draw a line of best fit. So the number one rule now, once you've plotted data, is do not connect the dots, please, oh please. And rule number 2 is do not force your data to 0, 0. Notice how the way I plotted this data, and unfortunately I just don't have a straight edge that I can use on this touch screen, but as I plotted the data, the line of best fit looks something like this. Right? And remember, a line of best fit is a line that goes through the middle. It's sort of a best fit of the middle of all of the data points. So you could argue maybe I should have made that a little bit steeper, but I think that's a reasonable estimate there. And on the AP exam, they're not looking for perfect, they're looking for a reasonable estimate. And now that I have an equation, what we need to do is first obtain some information for, now that I have a line, I need to obtain some information for that line. First thing we need, if we want to list here, is the slope with units. And so the temptation is to use 2 points, either a data point, like right here, or the y-intercept right here. Please do not use those things. For the data points, often like this data point, it is not really on the line of best fit, it's just close. And then for the y-intercept, it looks like it's at 0.05, but I don't know if it's really quite there. So instead, what you have to do is mark a point low down on the line, and then much further up, to reduce the uncertainty caused by estimating here, a point number 2. And what we need to do then is figure out, okay, what are the coordinates for this point, right? So this looks like it's at approximately 0.08 meters Always write units. This will help you when you calculate your slope with units. And then I'm at 0.35, so 0.35 seconds squared. So that's my coordinates for my first point. And notice how I use these intersection points right here with these grid lines, so that way I can better estimate. And that's out at about 0.46 meters. And the period is 1.75 seconds squared, the period squared. So now I have my y2, my y1, my x2, my x1, right? And so now to find my slope, I can do my 1.75 seconds squared minus my 0.35 seconds squared. Please, when you are doing your graph, get your points from your graph and calculate your slope from your graph. It drives me crazy on a lab quiz when I see these things, what I am writing here, then copied verbatim. So just a stipulation here, please don't copy my work. All right, so 1.75 minus that, and then on the bottom we have 0.46 meters minus 0.08 meters. And then we can calculate that, right? That should be 1.4 seconds squared divided by 0.38 meters. Hopefully I did that math right. All right. So that's my slope. But when you leave it in this form, it's not complete. Get an actual number. I don't know off the top of my head what is 1.4 divided by 0.38. So put it in your calculator and get an actual decimal number. So I only have 2 sig figs here, so that means that I'm going to round to 2 sig figs, and I get a value of 3.7 seconds squared per meter. That's my slope. The next thing we want to identify is what is our y-intercept. So on my graph, my value for b, it's the y value when x is 0. So that looks to be about 0.05 seconds squared. Don't forget your units. Now that we have that, we move on to the final piece that we need before we start to figure out what all of this means, which is the equation. In math, you learn that when something's linear, the equation's that. But that's a math thing. If I wrote that y here equals 3.7x plus b and reported that, somebody who's looking at this doesn't know what this equation indicates, except that the slope is 3.7. And I could put in the 0.05 for b, but otherwise it's not meaningful. So instead what we do is replace these things with the lab equivalent. So what I mean by that is, what is my y variable? It is the period squared. So the specific equation here is the period squared, and that period squared equals my slope for this equation, which was 3.7 seconds squared per meter. And then my x variable was my length, so times my length, and then plus my 0.05 seconds squared for my y-intercept. And now I have my specific physics equation line for my line of best fit. This equation should have predictive power, right? I should be able to go, okay, if I have a pendulum with a length of 2 meters, what should the period of oscillation be? Based on this equation, I should be able to find that. All right, now let's go ahead and work through the rest of the. So I gave you guys this sheet, and this sheet is supposed to help you work through what exactly should we write in terms of our conclusion for this lab. And I'm hoping that having this helps you to work through those steps here. And this isn't quite working, so apologies for the delay. All right, so the first thing, the purpose. What are we doing, right? What is the goal of this lab? The purpose here was to determine the relationship between the period of oscillation for a simple pendulum and the length. Determine the relationship between the period and the length for a simple pendulum. And again, always sort of shorthand here, or it'd be a little bit messy with the touchscreen. Apologies for that. So what is the thing that we changed, right? The independent variable that we changed was the length. The thing that changes when we make that length greater or less was the period. And then you talk about your predictions. So really, as you're conducting a lab, you always want to have an idea of how these things relate. This was more of an exploratory lab where you guys don't have much of a prior knowledge, but maybe you do. Maybe you've looked at grandfather clocks or other things. What is it that you expected to happen? All right. Now, usually in analysis, I'm not big and great looking for a specific thing there. Just what did you expect? Now that we've done the graph, this is the big thing here is what do we do with the graph and what do we do with the analysis? All right. So the first thing is what did we graph, right? We graphed period squared versus length. After we graphed it, we need to identify some important things. So the first one is, should 0, 0 be a point on the graph? Explain why or why not. And essentially what we're trying to do is think about, should that have been a point? Should it be that when my length equals 0, I should have a period equal to 0? And the answer is yes, ideally, right? And if we could somehow get there, that the length should be 0, if the length is 0, the period should be 0. Now the problem is that's not physically possible, right? You couldn't have a length of 0 because then we don't have a pendulum. So, you could sort of argue, is that really physically possible? I guess not. But so to answer the question, should it be a 0, 0? I mean, the line should go there, but no, because it's not physically possible to have that set up. That would be my argument, is it should go there, right? We can think about limits. The limit for the period as length goes to 0, the period should go to 0 too, but it's not physically possible. So what shape of the graph, right? Was linearization required? Yes, right? The original shape of the graph was a square root shape. So the shape of the graph was a y equals square root of x shape. So yes, what we did is we took the period and we squared the period. So now we did period squared versus length instead of period versus length. The next thing we want is our equation. Now ignore the plus or minus stuff for now. We haven't talked about how to find uncertainty yet, but that's what we just did on this sheet, right? This is our equation for our line of best fit. Period squared equals my calculated slope value times the length plus my y-intercept. So that would be our next step. So the thing we then want to figure out is what is the physical meaning of the slope and what is the physical meaning of the y-intercept. So let's start with the slope. And one of the suggestions I always have for you guys to help you figure out what is the meaning of the slope, you have two options. Either you already know what the equation should be, and so you can just say what you think it is based on what the equation should be. Or if it's exploratory like this one, we look to the units to start, right? The units right now are seconds squared per meter, which should look familiar if I rearrange this. This is the same thing as meters per second squared inverse, which is the unit for 1 over an acceleration. It's the inverse of an acceleration. So the first thing we could write up here for our meaning of our slope is the units are seconds squared per meter, which is the unit of 1 over acceleration. The next thing to point out is that our slope is constant. If our slope is constant, then something in our experiment must be constant that relates to this acceleration and relates to our experiment. So think about, what is it that causes the pendulum to swing back and forth? What force or action there causes that pendulum to move? And it is gravity. Right? So as a result, since the units are acceleration, and it has something to do with gravity, I'm going to say that this has something to do with free fall acceleration, which we talked about. In general, g is equal to 9.81 or 9.8 meters per second squared. Now, unfortunately, if we take the inverse of that, right, if we do 1 over g and put that into our calculator, so we do 1 over g, we obtain this value of 0.10 seconds squared per meter, and that's nowhere close to our slope. So in March, we will learn where this comes from, but for now what you could do is just go to Google and search period of a simple pendulum and see what equation we obtain, right? And you'll see these equations You can find it all over the place. We obtain this equation. If you look at your equation sheet for the AP Physics C exam, you will see this there too. Notice that it's similar to our equation. Right, so let's go ahead and write this on our little sketch pad here. We have this equation of period equals 2 pi square root of L over G. And this should look similar to our equation. So we would call the equation from our lab the specific equation, and we would call the equation that we just looked up, what would be the general equation, the equation that applies to all cases. Now notice what we need to do in the general equation is square the period, and so then we have to square the other side, and we would then obtain 4 pi squared L over G. Or I could rewrite that as 4 pi squared over G times L. So notice here then that I have this L and this L, this period squared and this period squared, and so this is the slope. So 3.7 should be close to 4 pi squared over G. So let's go ahead and put that into our calculator, right? If we do 4 times pi divided by 9.8, we obtain a value of 4.0. So not quite my value, but if we look at Excel, where it doesn't deal with the fact I'm using this touchscreen, look at that, 4.1 versus 4.0. That's really close. That's actually pretty great. You guys got pretty accurate, good data. So this slope here, what does the slope represent? The slope represents 4 pi squared divided by G. And we'll talk about where the 4 pi squared, as I said, comes from in March. But for now, the big thing is to recognize it's a constant. Its units are seconds squared per meter, which is the inverse of acceleration. Gravity is what's causing the swinging of the pendulum, and it's constant, just like the slope. So the slope is this. The big factor being G. All right. So the other things that we want to talk about then are the meaning of the equation, like what do we have, and the y-intercept. So notice that my y-intercept is not at 0, 0. It was at 0.05. So we want to think about what are some sources of uncertainty. There are standardized causes of uncertainty, or what we call standardized error, and then there's randomized error. So the question is, like, what sources are there? So an example of standardized error would be if for our pendulum, remember we had to measure the length, if we should have been measuring the length, if we should have been measuring the length all the way to the middle, but instead what you did is, I see what I keep doing now. Instead we measured the length just to the top. So that means that every measurement is off by the same amount. That would be standardized error because every single piece of data is off by that same amount. So if you don't have a y-intercept at 0, one of the reasons could be that we weren't consistent in how we measured. Maybe some of us measured to the top of the washer, some to the middle, some to the bottom. We were inconsistent. Or we were consistent in measuring to the wrong point. Another example of something that could cause a y-intercept not at 0, 0 is that we were timing the pendulum using our reaction time with a timer. Right? That's going to contribute just a little bit. If we're talking about 0.05 seconds squared, that's really not much. So a reaction time would be perfectly reasonable. Then we write the generalized equation, which this time we had to look up, right? Was period equals 2 pi, the square root of L over G. And then based on this, what do we have? We have an equation that gives us the relationship between the period of a simple pendulum and its length, right here. Now, I'm not going to write all this down, but this is the thought process you want to go to. First, we have an equation that gives us a relationship between the period of oscillation of a simple pendulum and its length. This equation tells us that the period is directly proportional to the square root of the length. Or the period squared is directly proportional to the length. That's the one relationship we have. So we saw that as we increase the period squared, the length proportionally increased too, and vice versa. G is a constant. If we went on a different planet, we would have a different value for that slope. But otherwise, the other thing that's important to point out here is that mass was not a factor, right? We had washers of different masses, and they didn't matter. All right, so that's the general process we go through for analyzing a graph. If you have questions, feel free to stop by, or I'll try to host a review session. Otherwise, lab quiz is on Friday, and thanks for watching. Have a great rest of your day.